Okay, so we've had a couple conversations now about isomers, and it's time, I think, to do a brief review. So first, I know you know this already. We got to say it. It's good to review it. First of all, there's constitutional isomers, right? In constitutional isomers, the difference between those was carbon, oxygen, carbon. I know I use this example every time, but where if these are all hydrogens, right? Then this is ethanol and boom, 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 dimethyl ether, right? So constitutional isomers is the first kind of isomer. Then the next kind of isomer is stereoisomers. And stereoisomers have three, we saw three instances. First of all, double bonds, right, could make stereoisomers. Rings could make stereoisomers. And chiral centers could make stereoisomers, right? So remember now with with all of these, if you had a mirror image, then this was called an enantiomer. Where am I doing here? Where am I here? Stop. An enantiomer, right? And if it wasn't a mirror image, then it was called what? Diastereomer, right? If you had a stereoisomer that was mirror image, enantiomer, not a mirror image, diastereomer. Now, I have good news for you. I'm not sure if this will be good news. I have news for you that we also have double bonds, rings, and chiral centers, which are neither. What? Okay, and that's what this section is about. So let's look at it. First of all, you have to appreciate, we've been talking about simple systems up to this point. What if we have something, what if we have a symmetric center or a symmetric plane inside a molecule with chiral compounds? Any compound with only one chiral center will be a chiral compound. However, with more than one chiral center, it's possible that you'll have a plane of symmetry, right? So look at these two below. These are definitely stereoisomers one of another, right? These are definitely right? Can you see what's going on here? So trans and cis 1,2-dimethyl cyclohexane in the Hayworth projection as we see it here, right? Definitely stereoisomers one of another. However, they're not necessarily chiral. And we're going to have to get used to using those words, right? So this is abstract, I know. So look at this. If we take the cis 1,2-dimethyl cyclohexane, you can see that there is a plane of symmetry, right? Look, can you see this? Can you see a mirror here? Suppose that's a mirror, right? If that's a mirror, you could see, hey, this methyl group might be looking over at the other methyl group and saying, hey, that's me, right? So since it has a plane of symmetry, that means it will be superimposable on its mirror image. It will be superimposable on its mirror image, and it is not a chiral compound. All right, so we'll be looking for planes of symmetry here, and you'll have plenty of practice. So let's look at it even more. Molecules with an even number of chiral centers and have a plane of symmetry are called meso compounds. Again, this is sort of redundant. If they have an even number of chiral centers and they have a plane of symmetry, right, they are called meso compounds. Okay? Remember the difference between that? Remember we had racemic recently? What was racemic? Racemic when you had chiral compounds, but you had a 50-50 mixture. Remember that? That's not what we have here. A meso compound is when you have a plane of symmetry. Okay? Another way to test if a compound is meso is to see if it's identical to its mirror image. Okay? So I'm encouraging here to draw the mirror image of the cis isomer and show that it can be superimposed on its mirror image. Okay? Whoops, whoa. Where am I here? Okay, by definition, when a compound is identical to its mirror image, it is not chiral. It is called achiral, right? A is the Greek prefix, which means not. Okay, so it is achiral. So if a I think that's the Greek prefix. If a compound has a plane of symmetry, it is achiral. But a compound that lacks a plane of symmetry may still be an achiral compound if it has a reflectional symmetry through inversion about a central point on the molecule, okay? In other words, if it's not just a mirror, right, internal mirror, but look at, you see here, can you see this reflects on that, okay? This reflects on that, and this reflects on that, okay? So this is a little more complicated. You might want to back the video up. Well, I can just rewind that, can't I? Z, right? Look at that. Can you see a reflectional plane of symmetry here? All right. So in other words, it's not. I've said plane. It's not a plane. It's a reflectional point of symmetry, right? So if we had like a point mirror, that would be going down behind the plane. That would be going across, and that would be going across. This is not chiral because it has a point of inversion. All right. So remember, the presence or absence of rotational symmetry is irrelevant to chirality. A compound that has a plane of symmetry is achiral. A compound without a plane of symmetry will usually be chiral unless there's like an inversion center. Okay, this is a rare exception. And I think that's it. No, we've got one more slide here. All right, so compound with chirality, I don't remember what this slide was. I'm going to look at it with you. A compound with chirality centers, but is achiral because of a symmetry. Yeah, this is also the review, right? It's called a meso compound if there's a plane of symmetry. So here, can you see a plane of symmetry? Like that red line be a mirror looking down on top of that, there's a plane of symmetry. Here's a plane of symmetry here, right? And here's a plane of symmetry, right? So those are meso compounds. And meso compounds have less than the predicted number of stereoisomers based on the 2 to the n formula because some of those siblings, if we can use that analogy we used earlier, are really identical compounds. All right. Good luck. Good practicing.